Welcome to the International Ozone Association's webinar, Ozone in Horticulture. My name is Tony Sacco, and I'm a Vice President of the International Ozone Association and a moderator for this event. Before the webinar begins, I would like to thank our sponsors for the event. Without their support, we wouldn't be able to have this presentation. Before we go into any additional discussions, my colleague Nicole Helms is going to explain some of the things that you should know to make this an effective webinar. Nicole?
Good morning, everyone, and thank you for joining us. As Tony said, there are a few housekeeping things to take note of. In order to make sure you receive the best audio, be sure to select the audio output in the audio dropdown. If you have any technical questions about the webinar's functions, please send them to staff in the questions box. If you have questions for the speakers, please send those in the chat box. Tony?
Thank you, Nicole. I'd also like to take a minute or so to talk a little bit about the International Ozone Association. The IOA is an educational organization that provides technical information on ozone and its applications through several resources. First, we have our peer-reviewed scientific journal, Ozone Science and Engineering. We have a news magazine, Ozone News. We have a website, which is shown on the slide. And we have technical conferences and webinars like the one you're attending today. We'd encourage you to visit the website, and if you find the information interesting, we encourage you to join us as a member of the International Ozone Association. The IOA is an international organization covering most regions of the world through 3 different groups. And membership provides access to a wide range of resources on ozone and discounts to attend meetings and exhibitions. Speaking of which, the annual conference for the International Ozone Association Pan American Group will take place August 15th through 18th in Las Vegas, Nevada. You can go to the website to sign up and learn more. Let me just quickly go through our agenda today. I will be giving a brief introduction to ozone, water, and gas treatment. Then a pre-recorded presentation from Jeff Martins on the use of ozone for vertical farming of leafy green vegetables. Buck Young will give a presentation on operationalizing ozone, lessons for agriculture. Dr. Saad Jassim, who is a former president of the International Ozone Association, will give a talk on ozone applications for greenhouses in Canada. And finally, ozone for fruit and vegetable preservation and storage will be discussed by Christiane Carboni. Thanks again for our sponsors. I will give a very brief introduction to ozone for water treatment. Besides being a vice president of the International Ozone Association, I'm also the managing director for Spartan Environmental Technologies, which is a custom integrator of ozone systems for a variety of applications, including horticulture. We're going to cover what is ozone, some key commercial applications, important properties of ozone, the components of an ozone water treatment system. Talking about applications for ozone, they cover a wide range of areas. I'll just note a few here. Almost 2 billion gallons of drinking water per day are treated with ozone. Almost All bottled water is ozonated prior to packaging. Many integrated circuits and modern electronics, including the processors that go inside mobile phones, are treated with ozone. Even denim and jeans that you might be wearing today have probably been treated by ozone. So what's ozone? It's the triatomic form of oxygen with the formula O3. It's a light blue gas with a strong odor. In Greek, the word ozine is the base word for ozone, means smell. After scientists noticed the smell of ozone, they started to try to understand what in fact it really was. It occurs in nature and can also be man-made. It's an unstable compound that must be produced on site to be used. It is more stable in air with a half-life of 3 days at 20 degrees C versus in water where the half-life at 20 degrees C is only about 20 minutes. Some of the key properties of ozone: it's an excellent broad spectrum biocide, a strong chemical oxidant. It can reduce toxicity of organic compounds, and it rapidly oxidizes certain inorganic compounds like iron, and can also be combined with UV and or peroxide to generate hydroxyl radicals to create an advanced oxidation process. I'm just going to focus on one of these properties in the limited time that I have available, and that is disinfection. Ozone works as a disinfectant by lysing microorganisms, as illustrated in the pictures to the right. Essentially, this causes the structure of the microorganism to break apart, killing it. One way to describe the effectiveness of a biocide is to look at what is called the CT value for that biocide. CT is the residual concentration times the time. And this can be computed by looking at the concentration of ozone versus the exposure time. And the area under this curve will give you the CT value. Normally, it's shown as milligram minutes per liter. This chart shows various bacteria inactivation by ozone as it relates to the CT value. So for E. coli, a value of 0.02 to 0.06 milligram minutes per liter will result in a 2-log reduction of that organism. Comparing ozone to other biocides, for the inactivation of Giardia, which is a encysted microorganism which is very difficult to kill, and viruses at the 99.9% and 99.99% or 4-log reduction levels. As you can see from the chart, ozone has the lowest CT values, which means you need the least amount of biocide or the least amount of exposure time to achieve the 99.9% and 99.99% reductions. So ozone can often be a good choice for disinfection. Now we'll talk a little bit about what an ozone water treatment system is and some of the key subsystems. The picture on the left shows the various components that would go inside an ozone water treatment system. First, you have to prepare gas that contains oxygen to feed into the ozone generator. Then, obviously, you have to generate the ozone. And because the ozone process generates heat, the system has to be cooled. Ozone generation output is proportional to temperature. So the higher the temperature, the less ozone you produce. Once you produce the ozone, it has to be mixed with water and dissolved to be effective in any application. So there's a technique for dissolving the ozone. Then you need the contact time, which was the T in our CT value. And because not all of the gas that's sent to the ozone generator is going to dissolve in water, you have to separate the gas from the liquid fraction. The liquid fraction, of course, goes to whatever process you're using. The off gas can almost usually be vented, and in some cases, because it contains a small amount of ozone, it might need to go to what's called an ozone destruct system. So some of the key design parameters for an ozone system are efficient production of ozone, efficient dissolving of ozone, system reliability, footprint, and of course, cost. One of the things I want to mention that's very important is that ozone is a irritant for people in their lungs, and OSHA limits the exposure of ozone gas to workplaces to 0.1 part per million by volume for a 40-hour exposure. So in other words, a person who works in an area 40 hours a week cannot be exposed to more than 1/10 of a part per million on average during that time. And most ozone systems will have instrumentation to shut the system down should those ozone levels be violated. This is an example of a fully integrated ozone water treatment system that produces about 70 grams an hour of ozone. The system size here is about 2 feet deep by 6 feet long and about 6 feet tall. And this is a system that was designed for a cannabis growing facility. So a system of this size can serve a fairly decent sized horticulture application. I'm now going to cover a couple of those subcomponent systems in a little bit more detail. So ozone generation requires a very dry gas to be used. Dry in this sense means minus 100 degrees F dew point. This means low part per million levels of water in the gas. The reason for this is that moisture can damage ozone generators, and moisture also reduces the generator efficiency and output. There are two common gases used for ozone generation. Air, which has been dried. This can usually produce ozone in the 1 to 3 weight % concentration range. And oxygen feed that can produce concentrations up to 20 weight %. Oxygen concentrators, which are similar to those things that are used for home health aid, except in larger sizes, can produce oxygen in the 90 to 95% range using the pressure swing absorption process. And this is fairly commonly used in ozone generation systems. Liquid oxygen can also be used, but normally for larger systems. The picture on the left shows a commercial PSA oxygen concentrator, and the schematic on the right shows the process for making the oxygen. Essentially, there are two absorber vessels. Each vessel contains a material called a molecular sieve, which absorbs nitrogen and water under pressure and releases it when the pressure is reduced. One of these columns is producing oxygen while the other is being regenerated. And then they flip back and forth. And this process results in a near continuous stream of oxygen in the 90 to 95% range. Once you have a dry gas with oxygen in it, you have to convert it to ozone. There are a lot of different methods for producing ozone. For example, UV radiation, electrochemical reactors, coronal plasma discharge. But these methods tend to produce either small outputs or low concentrations of ozone. The method that's used most commercially is the dielectric barrier plasma discharge, or silent discharge method. And I'm going to show a schematic of this system. Essentially, a high voltage electrode is connected to a dielectric. And then there is a gap between the dielectric and a grounding electrode. A high AC voltage is applied to the grounding electrode and the high voltage electrode. And as the oxygen-fed gas passes through the space between the two electrodes, micro discharges occur. And these micro discharges cause the gas to form a plasma. And in this plasma, some of the oxygen is converted to ozone. These pictures show a commercial horizontal tubular type ozone generator. The basic structure is a shell and tube heat exchanger, where the metal tubes are the grounding electrode, and the glass tubes that you see are the dielectric. A metal film has been deposited on the inside of the glass tubes, and that is the high voltage electrode. This particular system, each one of these generators shown on the right-hand picture, probably produces on the order of 2 kilograms an hour of ozone. So much larger than the picture I showed you previously. In the annular space between the dielectric and the stainless steel tube is where the plasma is formed. And this is a picture of an operating ozone system, and you can see the blue glow of the plasma. The next step in the process is to dissolve the ozone that's been produced in water. And a key parameter here is the ozone transfer efficiency, which is the percentage of ozone that dissolves, which we refer to as the transfer dose, divided by the amount that's produced, which is called the applied dose. This is affected by a number of parameters as listed here. The unbolded parameters, water temperature, ozone demand, and pH, are kind of the properties that the designer has to deal with. That's the water that needs to be treated. And the bolded factors, concentration of ozone, gas volume to liquid volume ratio, and gas bubble size, are things that are under the control of the designer to achieve the target. While there's a number of techniques that can be used to dissolve ozone, here's a couple of common methods that can achieve greater than 90% transfer efficiency. Venturi injectors, which require some sort of pumping action to create the mode of flow and the pressure to overcome the drop across the venturi, and fine bubble diffusers, which require a deep basin or tank with 16 to 20 feet of water over top of them to achieve the 90% transfer efficiency. The schematic on the left shows a side stream Venturi injection system, which is a common method of using ozone in water treatment systems. I'm not going to go into the details of this schematic other than to make two comments. First of all, it's important that the control system can maintain the mode of flow, inlet pressure to the venturi and outlet pressure to the venturi, because that defines how much gas can be drawn into the liquid. The other important control feature is to make sure that water never backs up into the ozone generator, because that would create severe damage. The picture on the right shows a small skid-mounted injection system without the instrumentation, but just gives you kind of a feel for what it might look like. So we have time for some questions. If there are any, I don't see any in the chat. So if there aren't any questions about this brief introduction to ozone, then we will move on to the pre-recorded presentation by Jeff Martins.
Good morning. My name is Jeff Martins, and I'm the Vice President of Sales and Service for H2O Engineering. This morning, I'm going to talk about the use of ozone for vertical farming of leafy green vegetables. First, I'm going to talk about the needs of the controlled environment agriculture market. Controlled environment agriculture is exactly as it sounds. It's taking produce from the farm fields and bringing them indoors. It includes greenhouses. It also includes today buildings where the plants are grown indoors with LED lighting. And the subset of that market that I'm talking about are vertical farms, where these leafy greens are stacked on trays, taking up much less space in an indoor situation for proper growing. After talking about the needs, I'm going to touch on the importance of filtration and disinfection and the interdependency of those two components. And then I'm going to talk about the advantage of ozone for indoor agriculture and touch a little bit on the vertical farm design requirements and H2O engineering capabilities. The market for indoor agriculture is on a mission to improve the lives of plants, people, and our planet. And one of the important components of indoor agriculture is that it's going to use much less water, as much as 95% less water. Basically, the water for irrigation, instead of being put onto a farm field, is going to be reused over and over again during the irrigation process. Another important component of indoor agriculture is that it uses much less land than conventional farms. It can be 97% less land than conventional farms. And that brings two advantages. One, instead of farming the leafy greens out in the field, exposed to the weather and all of the components outdoors in the seasonality, it's brought indoors, and in a controlled environment, it can be a perfect growing cycle. As we all know, leafy greens like springtime weather for growing, so indoors they can mimic the spring environment and grow leafy greens repeatedly throughout the year in a rapid process, much faster than on the farm fields. The other advantage is because it's indoors, these locations can be brought closer to major metropolitan areas and closer to the population that's going to be consuming the leafy greens. Some other advantages, we talked about water scarcity and using less water. We talked about using less land, but the indoor agriculture technology allows for growing leafy greens without the use of pesticides and herbicides. Basically, they keep the bugs from entering the building, and they keep the weeds from entering the building as well, so there's no need for pesticides or herbicides. And as we touched on, the supply chain challenges of transporting perishable foods across the United States to the populations that are going to consume them is reduced greatly because the farms can be located right in the heart of the big cities. So now let's touch on the water cycle in some of these vertical farms. And here is a kind of oversimplified schematic of how water enters the farm and is used in the irrigation cycle. So most of these farms, because they're located near large metropolitan areas, are using city water, and they'll take the city water and we can help them filter the water to get it pure for the nutrient mix. Then the farm will add a special nutrient mix that's just right for growing the leafy green vegetable they're looking for. Now, many of these farms will have 3 or 4 different grow rooms with 3 or 4 different nutrient mixes depending on the type of leafy green they're going to be growing. So this shows just one water system, but a farm may include multiple water systems in the same building. From the nutrient mix, the water moves up to the leafy greens that are grown in these vertical stack of trays, and the water cascades through and exposes the roots of the leafy greens to the proper nutrients for growth. Now, these roots can be in soil, or they can be just directly in the water itself, but the water flows through, carries the nutrients, and then it moves on to the next tray and cascades through the farm. The picture on the right will give you an idea of the scale of some of these vertical farms. And you can see that there's quite a few trays. The leafy greens are grown in a compact environment, and you can see how they can get quite a bit of growth out of a small space. However, as the water cascades through, it's going to pick up soil, some algae that's building up, some plant materials, some of the nutrients that might be precipitating. All of this is going to be cascaded through, and as they're reusing the irrigation water, these particles can build up. So proper filtration coming out of the farm is critical before the water goes to the irrigation reuse storage tank. Now, at the reuse storage tank is typically where we will dose ozone and recirculate ozone within that irrigation water to minimize the chance of pathogens growing or any fouling buildup caused by bacteria growth. And then that reused water, after it's cleaned, will move back to the nutrient mix, carrying many of the nutrients that are still in the water. It'll be topped off with nutrients and then sent back to the farm. So you can see from this irrigation reuse process, the nutrients are saved, the water's saved, bringing a lot of economies in the use of water and nutrients. However, it looks good on paper when simplified, but it is a challenging environment. When you think of this farm, these indoor farms, the temperature is just right, there's plenty of nutrients, and there's lighting, LED lighting, and it's a great environment for bacteria to grow. And so what we see is that algae, plant material, and soils start to build up in the water. And these will create a growing environment for bacteria and pathogens to kind of harbor and protect themselves within the water and make it harder to disinfect the water. And eventually, without the proper filtration, an outbreak is going to occur and the plant yield will deteriorate, right? So the yield, this finished product that comes out of this vertical farm, very critical to have good, fresh product, and any deterioration in plant yield has a direct impact on the profitability of the farm. If there is an outbreak, fouling tends to increase rapidly. This can get into a vicious cycle, making it very hard to bring back under control, and oftentimes will require a shutdown and physical cleaning. Now, that's why we say that there is an important interaction between filtration and disinfection. So in order to establish proper filtration, we want to make sure we have the testing that will lead us to the right technology and that we locate it in the right spot within the farm. Most farms in industry today have their own unique design which means the location of the ozonation and the filtration are going to vary from farm to farm. On the disinfection side, it's very important to make sure that we have the right dosage, that the ozone is mixed adequately in the irrigation stream, and that's why we use Maisie, Venturi, and mixing technology whenever we use ozonation. And then locating the ozone generator and the ozone dosing in the right location is also critical. So how do we know what filtration technology is best for the farm? We start with a particle size analysis to help determine filtration requirements. This is common in the industry. Here's an example of a particle size analysis report. You can see on the left-hand side, it'll show the size of the particle, and then the count of the particles, and the percent of total count. And from the graph, you'll see in this case that a majority of the particles have a 1 to 5 micron size as a percent of the total. It is a majority of the particles in the water. However, when you go to the bottom of the chart here and look, you'll see that the volume percent and mass of material and particles in this stream, in this irrigation stream, have a particle size of greater than 15 microns. So more than 80% of the volume of mass, of material and mass of material in the irrigation is greater than 15 micron. Therefore, we would need to establish the right filtration technology to account for both the mass and the particle size, to both avoid fouling of the system and also to have sufficient removal of the plant material so that we can lower the BOD in this irrigation water. So that talks a little bit about the filtration side. Let's talk about the advantages that ozone brings for disinfection in these farms. The first advantage is that ozone is a strong oxidizer. It's one of the strongest oxidizers, and that means it doesn't require a tremendous amount of ozone to bring bacteria, yeast, and mold under control. Right, so a lower dosage of ozone with a contact time of about 15 minutes in the irrigation cycle that will allow for proper control of bacteria and some unwanted yeast and molds like Fusarium and Pythium. The other advantage of ozone is that it doesn't build up a residual within the irrigation system. Ozone has a 15-minute half-life at a pH of 7, and there's no stabilizer because the ozone is generated on-site and dosed immediately into the system. So this half-life is a nice advantage in that you can add the ozone, you can use it to disinfect the water and the irrigation system right up to the plant, right up to the point where the water meets the plants, and then the half-life has allowed that ozone to reduce in concentration to a low enough point where it's not going to harm the plants. Now, there are some studies that show that even a low level of ozone can help with the roots' health and the uptake of nutrients. So a small amount of ozone concentration going into the plants isn't going to be too detrimental, but the farm can rest assured that the majority of the ozone will deteriorate through its shorter half-life. The other advantage is that there's no stabilizer in the disinfectant. So as the irrigation water is reused over and over, and the plants uptake the water and more disinfectant is added, that stabilizer, if they're from other disinfectants, can tend to build up in the water and cause two problems. One, it can have a direct impact on the health of the plants, and two, it can reduce the effectiveness of the oxidant if you have too much stabilizer in the system. And then the final advantage of ozone is that as it reacts and oxidizes bacteria, yeast, and mold, it will increase the oxygen because it degrades into oxygen and water. So that added oxygen in the water is beneficial for plant growth as well. So let's now go back to our farm design and talk about how we can create a proper design with ozone to greatly improve the health of the leafy greens. Let's start at the upper right, and that proper dose of ozone going into the system. Again, having enough to keep the irrigation lines clean, the nozzles clean, and the valves clean throughout the system, but a low enough concentration as to not impact the health of the plants. As the water flows through irrigation, it comes out of the farm, it's important to have adequate filtration of that water coming out of the farm and reduce the BOD that comes with the particles, the soils, the plant materials, algae, any bacteria that have started to build up in the system. All of that BOD will react with ozone, so it's important to remove as much as possible with adequate filtration. It keeps the whole system cleaner, it allows for better disinfection, and the farm can run longer on a growing cycle without having to shut down and go through a physical clean. After the filtration, the water goes to the reuse storage tank, and here it's important to dose a sufficient amount of ozone so that you have effective disinfection of the system. We've seen many farms that start with too low of a dose or too small of an ozone generator, and there's no way to catch up or recover from any type of system outbreak. Once the customer has a small ozone system, it's hard for us to upgrade into a larger system, and oftentimes it's a complete retrofit required to install an adequate ozone generator and ozone system for the customer. We'll often put filtration in with that ozone line to capture with a small 1 to 5 micron filter, bag filter, any particulate that might be created or precipitated out during the ozonation process. So that leaves the customer with clean, disinfected irrigation water for reuse. They'll take that back to the nutrient mix tank. There they will complement the nutrients that are still in the water, top it off, bring that profile back to what they're looking for, and send it back to the farm. And the last comment I'll make about the design of this system is that we want to make sure that the system is designed so that we don't dose concentrated ozone with concentrated nutrients. Many of the nutrient mixes include iron, and as we all know, ozone will react with iron. It will cause a precipitate, and if you have too much concentrated iron with concentrated ozone, you can you can create a precipitation problem, which can be avoided with proper system design. So that wraps up my review of the vertical farm and the use of ozone for keeping the irrigation water clean and disinfected. I'd now like to talk a little bit about H2O Engineering. We've been in the industry for more than 20 years, and we got our start making reliable ozone generating systems and have branched into the agriculture market about 10 to 15 years ago and have been providing benefits to the controlled environmental agriculture market over the last 10 years. With our systems, we can help control pathogens, help our customers reuse irrigation water, minimize maintenance that could be caused from biofouling incidents, and help our customers increase the dissolved oxygen in the irrigation water. To do this, we provide solutions that include feed water filtration, carbon filtration or reverse osmosis filtration in the feed water. We can help with the irrigation reuse in the way I just explained, with ozone disinfection, use UV disinfection as needed, some self-cleaning filtration systems to remove those plant, soil, and algae particles that build up in the water, and then also supplement with oxygen injection. And if the customer requires, we have systems for wash water reuse and rainwater filtration and disinfection. Our process for delivering a tailored solution is to start with an engineering design discussion. We'll connect our engineers with the farm engineers. We'll talk about the unique designs of that farm, some of the requirements, some of the challenges they've had, and we'll work with them to come up with a custom design system that will fit their farm needs. We'll help them build the appropriate equipment for that farm. We do the design build of a complete system so that in the end, we can deliver to that farm a complete ozone and filtration disinfection system. And we'll help that customer commission the system, and we'll be there to provide full service and support so that that system operates as designed for 5 to 10 years, 20 years after installation. We're there to build and support and deliver a tailored solution for our indoor agriculture customers. Thank you for your time. I'd like to.
So I think what we'll do is we'll move on to our next. Buck Young.
Hi, good morning, everyone. Let me know if you can hear or see my screen.
We can.
Wonderful. All right, so just by way of brief introduction, I'm Buck Young, co-founder and former executive director of an indoor hydroponic commercial cannabis facility, co-founder and CEO of an ag tech firm which develops and licenses intellectual property related to plant tissue culture, and a director of a public company which develops modular CIE and commercial vertical farming systems. I've been in the ag space for about 10 years now. Hoping to scaffold off of the previous presentation, but I think we're all coming at this place knowing that ozone can benefit our operations, and curious about what we need to know before operationalizing. So we're going to discuss 3 contexts in which an operator may choose to implement ozone. So the first context is pretty simple, a run-to-waste irrigation system. So this is field watering systems or with soil-based media and water only, no fertilizer through the irrigation system. Some of the challenges of these systems is, while drip irrigation is commonly used to enhance the productive potential of well-draining soils or where rainfall is insufficient while conserving water use, These systems can become fouled over time, harbor waterborne fungi or bacteria that may be pathogenic to your crop species. The risk here is that centralized irrigation systems mean that contamination in the water system inoculates the entire farm and cause large-scale issues for our operators. We're going to talk about biofilms in the irrigation systems and delve into the microbiology a little bit. Picture to the right here is sort of the life cycle of a biofilm, and biofilms are complex structures comprised of extracellular polymeric substances which firmly attach to surfaces and are embedded within heterogeneous cell cultures. So many different organisms living all within this extracellular matrix that they produce to protect themselves from the environment. They're notoriously difficult to remove once they're established, and they can harbor pathogenic microorganisms like Pythium, Fusarium, Phytophthora. They can also detach and form clogs, so-called sloughing in components like filters, emitters, nozzles, and anybody who's experienced aggressive biofilm knows what a challenge it can be. There are techniques to remove biofilm, and these can include physical means such as ice picking, which is pictured in the top there, and chemical clean-in-place procedures. But both such techniques are merely temporary, create significant operating costs. They're largely ineffective at reducing microbial loads long-term because they are a non-persistent antimicrobial effect. The chemical sanitizers, enzymes, and pH-based remediation is often inappropriate, either due to local regulations or waste product collection challenges. This is some of the challenges with persistent chemical treatments, as you got to clean up after yourself. So why ozone treatments in irrigation systems? Well, unlike chemical and physical clean-in-place treatments, ozone provides persistent, broad-spectrum, residue-less antimicrobial treatment, which is highly effective at preventing and removing biofilms. Most irrigation components are already ozone compatible, such as the silicone diaphragms and emitters, plastic PVC and PEX piping, stainless steel, particularly 304 and 316 moly, which is found in tanks, fittings, ceramics and silicate filters, bronze and brass pumps, and high density, low density polyethylene tanks, stakes, and emitters, many of the common irrigation tools that we rely on. But there are things to consider. The sizing of the generation for intended flow rates and, it's important to work with your integrator to size the generation for the intended flow rate and give consideration to the zone design and the duration of irrigation events to ensure that there's persistence at the line if desired. Ozone levels which provide plant promoting effects but not induce phytotoxicity, refer to the literature to find what those may be for the crop that you're working with, and avoid ozone incompatible materials such as cast iron, carbon steel, nylon, so forth. The second context we're going to look at is the run to waste fertigation system. And so this would be hydroponic fertigation where the aqueous fertilizers are present, primarily in soilless media. And so these systems are especially prone to aggressive biofilm accumulation because the fertilizers are present. They can feed the microbiological communities. And so there is no resource limitation other than space to colonize within the pipes. The clean-in-place procedures become less effective because the generation time for these biofilms is increased in the presence of nutrition. And if you get particularly bad biofilm accumulations, even cleaning can become compromised by the sloughing and clogging in the system. So it's important to stay on top of the microbiology inside your irrigation system when you've got water-soluble fertilizers. And so ozone's reactive potential can have impacts on the fertilizer constituents. So there's really three approaches if you're using a fertigation system that you could consider. Approach one is a pre-fertigation ozone the fresh water, so just keeping the source water clean, and with removal of ozone prior to the addition of fertilizer. Now the pros there is you've got clean source water upstream for your contamination, and you don't need to make any adjustments to your fertilizer recipes to account for the reactive potential of the ozone. The con is that CIPs will be required downstream of fertigation. Approach 2 is to alternate the fertigation and irrigation with ozonated water to provide end-of-line antimicrobial treatments to all aspects of the system. So approach 2 is giving you intermittent antimicrobial effects post-fertigation, which can provide effective, particularly if the lines are free of biofilm, this can be a way to maintain them. But the irrigation versus fertigation events can flush nutrition out of your root zones. There's particular need to monitor your root zone ECs, and many operators working with rock wool, for instance, will implement these flushing of accumulated salts anyways. And so just thinking through the volumes that you need to deliver so that you've got the persistence at end of line to assist with this. And approach 3 is to manage the chemical interactions of ozonation. And we'll discuss this in greater detail in context 3, which is the recirculating fertigation system. But this is, the holy grail, if you will, the continuous antimicrobial effect to all aspects of the system. But it's going to require some monitoring and adjustment from your standard fertigation schedules. And some supplementation, as well as some design considerations to decrease the potential, the rate of reaction between ozone and the fertilizer constituents, which we'll discuss. So here's context 3, the recirculating fertigation system. So this would be a nutrient film technique or mediatorless system. For operators that are sustainability focused, water constrained, or those which may have high wastewater disposal costs. So these are really where industry is moving towards. However, effluent collection still presents a major vectoring threat. You can imagine if you've got pythium in one part of your system, you collect it in a central return. Next thing you know, you're inoculating your entire farm. And so where we see these systems currently is typically crops with short crop cycles, which allow an operator to decontaminate the system fully between cycles at a regular interval. Let's talk about the interactions between ozone and fertilizers. Micronutrients such as iron, manganese, as well as other transition metals, which are highlighted in yellow on the periodic table, including nickel, copper, zinc, moly, and others, are subject to oxidation from ozone. These are incomplete valence shells and highly reactive with ozone. So the oxidation of these metals form complexes which prevent uptake by the plants. They're no longer bioavailable. However, it's worth noting that the macronutrients, your NKP interactions, are not a concern when using ozone. Those are constituents in high concentration, which ozone will not have any significant impact on. So when we're trying to manage the oxidation over micronutrients, many fertigation operators are already using chelates to help increase the stability and bioavailability of micronutrients. And so many water-soluble fertilizers already are complexed with things like EDTA, EDTA, and so these molecules can lower the rate of reaction. The literature also has examples of micro and nano bubble encapsulation of O3, which can reduce the rate of oxidation and provide better end-of-line antimicrobial effect. So the having these sort of stable, small encapsulated bubbles reduce the surface area and the potential for interaction between O3 and your nutrients. It's important to consider conducting leaf tissue analysis to be monitoring what you're actually taking up in your plants when implementing ozone sterilization. So leaf tissue analysis, leachate collection. Some of the challenges with these recirculating systems is there isn't real-time speciating assays to tell you what's in your water chemistry and what form it's in. And so even water tests can be somewhat misleading if you don't know the species that your particular element is complexed in. So just things to consider, and ultimately let the plants tell you what they need. If you're, and there are certain tips and tricks we can get into the Q&A around foliar feeds and timing of feeds to make sure that you're hitting those key crop development milestones with the complement of nutrition that you need. So I thank everyone for their interest, and happy to take questions at this time.
Nicole, did you see any questions for Buck?
I do not.
Okay. Well, Buck, you mentioned here at the end of your talk that there were some things that you would have addressed in the question section. You have some time. Why don't you go ahead and tell us, what your thoughts are?
You have to jog my memory there. I forgot exactly what I was referencing to. Was it the ozone bubbles? I think I talked about it a little bit more. There are techniques I'm sure many integrators are already working with to increase the dissolution of, increase the solubility of gaseous ozone in water. But I think there's a value in looking at some of these products that produce a nanobubble with a gaseous interior as a way of decreasing the surface area of the ozone. There are products that I've seen that are made out of carbons, which I don't believe are ozone compatible, but some of the ceramics, so you've got a porous surface, you're pushing high pressure gas through that surface, and you've got a shearing velocity of water that is sort of ripping that bubble off as soon as it can and getting a very small particle size. So the smaller the particle size or the bubble size, the more persistent that bubble is in suspension. So it's sort of a bit of a balancing act, and it's got to be sized for your system. You certainly want some dissolved ozone to facilitate the upstream portions of the system, but having a portion of the ozone remain in that gaseous encapsulated bubble allows it to interact later on time and distally from the irrigation, from the fertigation system. I think that's an opportunity for sophisticated operators to work with their design and engineering teams, to really find a bespoke, engineered and empirically tested solution, to keeping your systems clean. It's anybody who's worked in the space can attest that this is a persistent challenge for anyone. No operator is immune from having a pathogen enter their facility, even if you've got great biosecurity. And these fertigation systems, unmanaged, can become catastrophic. In my career, I've experienced that, and ozone was the way we got ourselves out of that trouble. But it did take us some time, and it's always better to be on top of the microbiological aspects rather than addressing them in the heat of the moment. So if you don't have it, start thinking about it. If you're thinking about an operation, build this into the core of your irrigation system design, it's going to save you and your team so much headache down the road. Can't emphasize that enough. I've described ozone as an essential element of commercial fertigation.
Okay. I think there are some other people that want to ask questions. Nicole, can you allow them in?
People who have their hands raised, yes.
Okay.
Let me try to unmute here. Okay, I've sent a request to unmute Adam Doran.
Hey, Buck. How are you? We know each other.
Hi,
How are you? I'm just seeing, do you see potential for water reuse applications with ozone in cannabis, be it fertigator or runoff water, condensate water, that sort of thing?
Yeah, absolutely. I mean, the condensate one is interesting. Ozone is often, I think we heard in our earlier presentations, used to remove some metal. So like iron in condensate return is common, and so ozonation of that water can remove the iron. Or if you've got groundwater with high iron, I've seen that as an application as well. For the recirculation of the effluent, this is where we're really interested in the biocidal aspects, but preserving the target nutrition. I mean, I'm not sure everyone is operating at the level where they're doing leaf tissue analysis and adjusting their fertilizer recipes on the fly. Many standard formulated fertilizers are sufficient. But if you've been using that particular system for a while and are going to implement ozone in a recirculating system to try to increase your water use efficiency, there will be differences. It's not a simple, turn it on and go. You'll start to see micronutrient deficiencies if you're not adding more chelates or supplementation. As I mentioned, the foliar is an opportunity as well. If folks are overhead watering, that's a great way to get some of these more difficult to uptake, calcium, magnesium. Foliar feeds are effective that way. It is. I would say it's not without challenges. It's worth developing a team that can do that nutrition optimization so that you have the evidence basis for knowing that you're operating at peak performance. But as I say, there aren't these tools to give you sort of real-time insight on what's coming back to your system. And so the way to address that is to simply scale up so that the volumes that you're collecting and returning are sort of, if you will, diluted by what you're adding back in, and getting you closer to your target. Or you could be collecting, testing, determining what's in your leachate, topping up, and then adding back into your system if you had a large enough collection and reserve to give you time to run that water sample to the lab.
That's a fantastic answer. Thank you, Buck.
I guess we could try to unmute Mohammed.
Yes, one moment, please. I'm having some problems getting his audio to request.
Just while you're doing that, I'll just add, Adam, particularly if you're doing leachate collection and reprocessing, let's say 70% of your irrigation or 70% of your irrigation or more is going to be collected through your condensate in a closed environment. And so you're getting, that's probably the best opportunity for water recapture and reuse rather than collection of leachate.
Makes sense.
Okay. Let's, I saw that David McKay was able to unmute himself. You have a question, David?
Hi. Hi, Buck. Thanks for this presentation. I put some questions in the chat, but I'll ask them to you verbally. How do ozone microbubbles help in this application?
Yeah, so so a microbubble is going to, if you think about the volume, so the interaction of the molecules, so you've got ozone in a gaseous form and encapsulated enamel bubble. The number of potential interactions goes down just because the ozone is not touching the ions in the water. You know, it's partly why ozone's half-life in air is different than its half-life in water. You know, and so having gaseous ozone encapsulated in a bubble in your irrigation system versus dissolved ozone that is bumping into every molecule and with a higher rate of reaction means, you know, in our system, when we started supplying dissolved ozone water to our fertigator, once we added our fertilizers, it was very difficult to detect ozone at that point, just because it reacted immediately. Now, it did leave us with hyperoxygenated water, which has its benefits, and you know, it can also feed biofilms. But we ran into an issue where we kept our fresh water clean, super oxygenated. We then put in fertilizers with no antimicrobial treatments, and we got biofilm explosions because there was all the oxygen, fertilizer, and space for biofilms to just take off on us. And so then we went to that sort of that intermittent, where we were at least getting periods of persistent ozone down the line with straight water to keep the biofilms down, and then irrigating or fertigating the rest of the time to feed our plants. It's sort of a hybridized model there. But that gave us more concern to monitor the ECs and chemistry in our root zones. You know, so the bubble is as a technique. You know, you're still going to get dissolving from that bubble into water, but absent ozone, some of these nanobubbles can persist for 24 hours in solution, in suspension. You know, so I think it's an area that is essential to unlocking the value of ozone in recirculating fertigation systems.
So we have some, David, if you could mute yourself again. We have some additional questions in the question sections. It's difficult for me to read the questions, but one of the questions is, do you have a chart for the correct amount of ozone that's required, given, you know, whatever important parameters that you have?
That's a good question. It's I would say this, it's a bit bespoke, right? Because it depends on where you're measuring that ozone concentration level. And it depends on whether it's persistent or intermittent. You know, and it also depends on the microorganisms that you're concerned with or dealing with. And so there isn't fortunately, there's not like a simple answer to that question. You know, in our system, you know, we had, let's say, half a ppm in our freshwater tank. And that was sufficient for remediating what were pretty bad biofilms in a reasonable period of time. After that, we dropped that down. You know, but in cannabis, where this implementation was done, you know, we see plant promoting effects at the 1.5 ppm level. Really, it was more a function of what is the minimum dose that we can provide for maintenance of clean lines without, you know, and minimizing that impact on our water chemistry, so that you know, we can prioritize nutrient optimization in a in a clean system. So I think bumping up against phytotoxic effects is unlikely, partly because end-of-line concentrations are always lower than upstream, depending on it, particularly as your system gets bigger. Also because as soon as you sort of drip that fluid out into your media, I've read studies that suggest it's really not even penetrating more than 2 centimeters into like a rock wool media, which has a high matrix potential. And usually those are sort of empty spaces in the media anyways. The top inch of your rock wool is roots are usually not present. So the phytotoxic stuff I don't think is a big concern unless you were applying like remediative doses of ozone in crop cycle. Now I'm speaking about cannabis, and I just encourage everybody to look up your particular crop to understand how it may respond to ozone, because my experience may be different.
Thank you, Buck. I think we'll close the questions here. I think we have Buck's contact information on his slides.
It's not on my slides, but I'll send, Nicole can provide it.
Okay, so if people who have questions, we will provide you with an opportunity to send those to Buck. We'll now move on to the presentation by Dr. Jassim regarding ozone use in Canadian greenhouses. Saad?
Good morning, good afternoon, wherever you are. It's a pleasure to be here for the presentation for the International Ozone Association. And the presentation is going to be about the application of ozone for greenhouses in Canada. And
Could we hold on 1 second, Saad? Nicole, Saad, have you given his screen to be presented?
Yes, he has access now.
Okay. Saad, you can go ahead and show your screen.
You see it now?
Yes, we can. Thank you.
Okay, thank you. So basically, as I indicated, the discussion we have here about the application of ozone for the greenhouse industry. Sorry. The first thing I would like to acknowledge the land where we are, where I am presenting from. We gather this traditional in this traditional territory of the Council of Three Fires, the Ojibwe, Ottawa, Potawatomi, and the Huron-Wendat peoples. We are dedicated to honoring Indigenous history and culture while remaining committed to moving forward respectfully with all First Nations, Inuit, and Métis people. Okay, so the application, 1 second here. Okay, the application for the greenhouse in industry in Canada mainly focus on the vegetables, and it's a big sector, one of the largest growing sectors in Canadian horticulture. And the farming for the greenhouse farming produce agricultural products, and it's been quite useful due to the ability to provide products that is available when the usual products are not available, and that would reduce the prices that could go very high if you don't have enough available. And usually these are grown in a controlled environment, heat, water, nutrients, and employing some artificial lighting. And we're gonna, as now it's been a very applicable thing in the cannabis greenhouse. This method of farming requires a good investment in infrastructure and the use of some of advanced technology, and have a good understanding, because if you don't understand how the new technology or advanced technology is used, you could have some problems in the operation. And back in the early 1990s, Canada has emerged as one of the leading producers of greenhouses in North America. And later on, the United States and Mexico are playing also a major part in this region to provide the vegetables like tomatoes, cucumbers, and others. And Canada is also one of the only North American countries that provide an annual government statistic of the greenhouse production. For some reason it's not moving. Okay, so stewardship for healthy crops. The importance of applications of the nutrients, the disinfectants, and application of new technologies and innovations made the operators make sure that are aware of the specialized integrated pest management IPM programs available to produce products that is healthy and applicable to put in the market to produce and continue to produce them. The healthy crops require multiple strategies. You need to look at preventing any diseases entering the system, because you could lose in millions of dollars if you have a problem, and I've seen it in some of the applications, because of the lack of monitoring and the devices used in these applications. So also you need to look at the biosecurity of the plants, and especially now with the new applications of cannabis, the security is very tight, and it is understanding that is some kind of products need to be monitored. The use of traditional pesticide products now is becoming very limited, because growers are now looking at some new applications and to be accountable as an environmental stewards, and also good neighbors. Don't impact the community. Many of the greenhouses are within the living areas, so the people there, you don't want to produce products and waste that could impact the neighborhood. The production, as indicated, is scheduled, so the new plants come into production when the domestic field crops are still months away. Around early December, after an annual complete cleaning, the greenhouse, and then you prepare for that. The plants are brought from propagator and placed along rows of growing media, and we've seen it in different slides with the previous presenters. In midwinter, the days are longer, of course, so the production begins and continues through the summer and fall. So the industry has been growing substantially in Canada, and total number of employees are increasing, and it's been very stable over the 5 years. Of course, we have some issues in the last 2 years because of the pandemic and the impact, especially on the seasonal employees. And what does that mean? Basically, seasonal employees are working certain time of the year, not full time. Currently, as of 2019, according to statistics, 12,492 people employed by greenhouse industry. 7,347 are permanent, and the seasonal employees are 5,145. Ontario is the biggest province in Canada, about 14 million population, and is accounted for about 66% of the total number of the greenhouse employees in Canada. So in 2019, there were a total of 838 commercial greenhouses, vegetable operation, with 17.6 million square meters of production area, which produced nearly 664,450 metric tons of vegetables. And there is a steady increase in greenhouse vegetable production, an increase in numbers, and in fact expansion of the sizes as well. And acreage now is about increased from 21% over the last 5 years, and 48% over the last decade. So Ontario again continue to representing the largest greenhouse and representing 69% of the production, followed by British Columbia and Quebec, which are 18% and 6% respectively. So ozone is one of the strongest oxidants used successfully in the water treatment, as Tony and Buck introduced prior to my presentation, and removes fungi and bacteria and viruses and controls biofilm. And ozone is unstable gas, and what that makes it is more strong and active in oxidation, and decomposes to oxygen, can be improved to improve root health. And you need to have a proper design for the system in order to achieve the required treatment objectives. This is how ozone, you've seen some similar slide before. The oxygen molecule has 2 atoms, and with the direct discharge, you break it into 2 atoms. One of the atoms attaches itself to another molecule of oxygen to produce ozone, which is 3 atoms molecule, a very unstable molecule, which is very active. And similar to a table you've seen before, this is a chart to show if you use ozonated water, chlorine or chloramine. And what does that mean here? These figures, 1.43 milligram minute per liter, and we use the CT calculation here. And this study was done by the Waterworks Research Foundation, and looked at CT values for 3-log inactivation, which is 99.9% of Giardia inactivation at 10 degrees and pH 7. So to make it simpler to understand it, if you have 1 milligram per liter of ozone or chlorine or chloramine, what does that mean? You need 1.43 minutes to achieve this inactivation goal of 99.9% of Giardia, compared to 112 minutes if you use chlorine, and 1,850 if you use chloramine. That is if you're using ozonated water versus chlorinated water, or water with chloramine if people the city water is that, and you just add use it as is. So that, what does that mean? The shortest time means the smaller physical size or size of the contactor, and that is reduce the construction costs and infrastructure, and reduce footprint. Reducing footprint is important for climate change because of the heating required for the area and all that. So many advantages here when you have a quick, and also if you don't have the size of the acreage required or the land in some locations, like for example British Columbia, you need to cut trees to place any industry, and the public is not happy with that. And also for climate change, you don't want to cut trees. So this is a key issue in reducing the footprint for the application. And we're going to have a case study we had for implementation of ozone. I was involved in that one, and with a greenhouse called MCM Acres Limited, a successful greenhouse application in Leamington, Ontario. And Leamington is one of the most populous with the greenhouses, and the size of the operation 14 acres, and each acre is 4,000 square meters or 43,560 square feet. MCR Acres produce high quality tomatoes and is well liked in Canada, United States, and they deliver it regularly for a few years. In 2004, the plan was to increase from 10 acres at that time to 14 acres by 2004. So the owners started to think about it, and they were using 450,000 liters a day and discharging 110,000 liters to Lake Erie. And we know what is the problem with Lake Erie now. And you see here the diagram shows this is Leamington, this is Ohio here, and we know what happened in Lake Erie in 2014 with the algal bloom. So discharging that much, and there's many of the greenhouses here in Leamington and some in Kingsville as well. And also further up, if you go to Niagara-on-the-Lake, there are other many greenhouses here. There's a huge concentration here, and there are some greenhouses, according to my knowledge, to exceed 50 or 60 acres. And so this is the MCM Acres Limited, the owner, Mr. Mike Mastronardi. He approached us when I was in charge of the water operation for the city, the water, and we had ozone installed in 2001. It was the first application for a municipal system with ozone as a primary disinfectant. And we supply at that time close to 240, 250,000 people. So he approached us and he came to the water plant and he was impressed with the system he saw. And after discussion with him, we were preparing at that time in 2003 to go to the International Ozone World Congress, and it was in Las Vegas. So he agreed to come to the conference. So he went to the conference, he attended sessions, he went into the exhibitors area, and he was impressed to see the technology and how far the water industry is going with the application of ozone. And you see here in the picture, this is Mr. Mike Mastronardi, that's MCM Acres, and this shows a picture for the area involved. And and after the conference, and we had a few discussions and meetings, Mr. Mastronardi, he agreed to put ozone, and he contracted SJ Environmental Consultant, which is my consulting business, to do the design for the reuse of the discharge wastewater, because we talked about the impact, and they were seeing the algal growth and the algae, how it's growing in Lake Erie. And also you save them quite a bit of money by recycling water and some of the nutrients. So we worked on that and reducing the wastewater. So we work closely with them, and we looked at, visited the place, and I had electricians coming to me as well to look at what's the electrical capability of adding the system needed. And so we did a good review to the site and looking at how can we do that. And the interesting thing was the MCM Acres had 2 underground concrete basins, and they were not in use yet. So when I went there, I went down there and I walked around, and I said, wow, that is a real opportunity for an ozone contactor. So I discussed that with Mr. Mastronardi, and he agreed. He was so passionate for the work and need to do a great job for the operation. So the basins were a good size, like each of the tanks were 27 meters in length and height, about 2.7 meters, width 12 meters. So I did the design calculations to, and I based it with the information available at that time. We worked on the design with a CT concept, and I used a GRD inactivation, which is way on the safe side for doing that applications. Also, I introduced the suggestion to include baffles to improve the inactivation because of the inactivation factor credits. If you have baffles, it will be way better and use less ozone to achieve your goal for disinfection. And they agreed on that, and they were installed. 316L stainless steel baffles. What you see here is the nutrient storage. So it's a good size application here. So the ozone system installed was MCM. They purchased the Dell Ozone CD130, and based on our recommendation, they did 2 ozone analyzers and also a dissolved ozone monitor, an ambient ozone monitor for safety for the staff, and also an ozone destruct unit as well in the area. So we designed a system that is safe and you can monitor the application quite well. And we did grab sampling, and also we have a HAC DR890 colorimeter for ozone, dissolved ozone, and we were doing sampling regularly in order to do that before we start the application. And this is, excuse me, that's the ozone generator. That's in general ozone system with monitors and all that. And this is the 2 basins, you know, and you see the baffles, and we monitor the ozone in that area to see how much you don't want to have higher concentration of ozone to go into in the irrigation system. The dosages in average were about between 1.5 to 2 milligrams per liter. And residual was monitored at the second ozone contact, as I indicated, and approximately 9 minutes time of flow when the water and ozonator enters the system, and you add the water to it. So ozone dosages were maintained at the monitoring in the second, which is at almost the beginning, about 0.3 milligram per liter, and we make sure that the water comes to irrigation way less than 0.1 milligram per liter. Rarely we were seeing 0.1. That means good disinfection is taking place. Temperature was maintained around 15 to 20 degrees centigrade, pH around 5.5, and you see this is during the application growth, a healthy system is here going. And here we're monitoring, we're looking at the tomatoes growing, and that we're doing some work on the ozone generator here. And as you see, a very healthy product, well liked. In fact, locally, there are many of the local people, they were taking the product, city of Windsor and the areas around it as well. Then after that, I was invited to give a talk about the application, and here I'm having the tomatoes from the greenhouse itself at the ozone conference. So it was at the greenhouse international conference in September. It was at Niagara-on-the-Lake. And you see here, when we are reducing the wastewater going there, this picture is in satellite picture in 2011, and you see still there's a problem. There is a lot of nutrients going from both sides, Canada and United States, and that's why that caused the problem, as we know about the harmful algal blooms that caused the problem in Toledo, Ohio in 2014. And in 2012, I was involved with the International Joint Commission as the director of the Great Lakes Regional Office, and we did 8 public meetings, 4 in Canada and 4 in the United States, alarming everybody, the public, governments, industry, farmers, about this issue, about the discharge of nutrients and the issue of the cyanotoxins. But apparently nothing happened, and 2014, city of Toledo was hit with the cyanotoxins and caused the problem that everybody know about. Other applications now, it's increasing in Canada, which is the cannabis in greenhouses and outside as well. And because the government approved the Cannabis Act to allow to use it within certain limits. And basically the framework for that is to control the cannabis for sale, possession, production, distribution. And by October 17, 2019, production and sale of edible cannabis, cannabis extract, and cannabis topical became legal in Canada under the Cannabis Act. So the purpose of the Cannabis Act is to prevent youth from accessing cannabis, displace the legal cannabis market. Protecting the health and safety of youth is a top priority. The Cannabis Act established serious criminal penalties for those who sell or provide cannabis to youth, use youth to commit cannabis offenses. The Cannabis Act also protects public health by setting rules for adults to access quality controlled cannabis, and also creating a new tightly regulated supply chain. And you see here the graph shows the increase in cannabis from in the years, and from 2018, 2019, and 2020, and it's growing further now after 2 years. And you see the growth in the greenhouse, and this is also combined, and this is now the outside as well. So the big industry coming up, and there are over more than 50,000 of a greenhouse industry operating in Canada, in Ontario especially. That concludes my presentation, and if there's any questions, I'll be more than happy to answer.
Thank you, Saad. So we have had a couple of questions.
Okay.
But they're not really necessarily just for your talk, Saad. They're more general questions. I think that maybe if Buck is still on the line, he might want to weigh in a bit too. I will start out. The first question was regarding the use of AOP. And I think it's important to point out that when we say advanced oxidation, we're referring to the production of hydroxyl radicals. And hydroxyl radicals are a stronger oxidant than ozone, but they're also non-specific, which means they'll attack anything. Whereas ozone is a specific oxidant, slower reacting, and lower oxidation potential. So use of advanced oxidation may or may not be appropriate in all applications. Buck, are you still on the line? Have you done any work with advanced oxidation in cannabis?
I mean, I can't claim to have the expertise that I think you're hoping that I have on this subject. Maybe Dr. Jassim is more positioned for this.
Well, with the advanced oxidation process, that could be many applications. You could be ozone plus hydrogen peroxide, or ozone plus UV, or UV plus peroxide. But you need to make a good distinction. What is your goal? And you don't need to add, because ozone can do the job here without the need to access into it, because you're adding additional application. One of the challenges for the peroxide is the shelf life. You can't bring small amounts every week, because the delivery cost will be more than the amount used. So that's why you need to be very selective, and you do enough tests to find out if ozone was good enough to do the job. And for that application, when we looked at the sources of contamination, ozone was more than enough. And we did some on the side scale application, small scale application, and you found improvement on the water and cost settling as well when you add it, and that helped in the tanks that we had to have some settling on some of the contaminants that could be, or even some of the, because if you have some of the soil, some of the contaminants might be attached to that as well. So ozone by itself was able to do the job, because if you add hydrogen peroxide, you basically need a tank, pumps, monitors, and also when you receive it, they're selling to you the highest concentration most of the time is about 50%, but when you get it, by the time it's being shipped to you, it's down to 40 or 43, something like that. And we've seen it even with small containers when we did it in lab tests. So that's why you need to be very specific. If you don't need it, you don't have to. And I haven't seen in Leamington anybody using advanced process, because ozone was more than enough to do the job.
Yeah, the other point I'll bring up is that the half-life of hydroxyl radicals is incredibly short, orders of magnitude below those of ozone. So it's not a chemical that could move throughout any kind of system and provide.
Well, usually with the hydroxyl radicals, it's produced when you have that application. So you're not storing the water with after you apply to that. But the thing is, as I said, you need to see is there a certain contaminants that you think ozone is not able to oxidize? Then the hydroxyl radicals will play the role.
Okay.
And that's what it is, yeah.
Yeah. The next question that came up, again, either for Buck or Saad, is dealing with aflatoxin. Does anyone have any experience there?
Which toxin?
Aflatoxin?
Aflatoxins? Yeah, I mean, the aflatoxins can be very difficult to remediate from products because, you know, they may be stable to gamma radiation, as an example, or other remediations of final products. You know, I think there was a lot of concern over aflatoxins in the cannabis system because the original contract Health Canada used to produce cannabis back in 2000 was done in a mine shaft. And so you can imagine not the most ideal environmental control system. I think there have been no reported instances of aflatoxin in cannabis under the Cannabis Act. You know, but with any of the sort of products of microbiology that may be toxic, it's better just to address the agents that are producing those mycotoxins than trying to remove mycotoxins. So clean germplasm, clean irrigation system, clean environments should prevent that from being an issue. But I think our next speaker, Christian, may have some comments on storage and, you know, keeping products from decaying and producing mycotoxins.
Okay, one last question, and I'm not familiar with this at all. Botrytis, are you familiar with that material?
Yep. In cannabis, botrytis is commonly what's thrown around as the term to describe bud rot. We ran a BSL level 2 microbiology lab and did pathogen sampling and isolation from other cannabis operators, so I have a good sense of what's going on in industry. Primarily, the bud rot that folks are experiencing is associated with an endophyte called Fusarium proliferatum or Fusarium oxysporum that travels, that lives in tissues, is carried when you clone plants, and can express both on the media and then sporulate and land in floral sites, but as well as working its way up through the plant tissues and expressing in those floral nodes where there's low airflow and high humidity. Again, you know, a clean irrigation fertigation system is essential to decreasing the level of this, because obviously it's a big issue for an operator who can't see inside the flower if a consumer is getting a chunk of bud rot. So cleaning up the system, cleaning up germplasm is the technique we use to address that.
Okay, well, thank you very much. I think we will move on to our next speaker, our final speaker, Christian Carboni. Christian, are you available? There you go.
Okay, thank you. I hope you can see my screen now.
Yes, we can.
Super. I'm Christian Carboni of Industria De Nora. I want to thank International Ozone Association for this opportunity to make this presentation. It is a pleasure for me to make this presentation and stay with you. I'm the last speaker, but I hope your mind still have other space for other information. Fortunately, the speaker before mine was very interesting. In some slides, I discussed about mycotoxin. I understand back. I fully agree with the back that it's better to prevent that not remove the mycotoxin. There is some test removing mycotoxin in wheat and corn and so on. In fruit, I present later some results how you can manage and prevent the formation of mycotoxin of apple and other products in post-harvest.
Christian,
Lost
you're
your
on
audio,
mute.
Christian.
Christian, we lost you if you're there.
Can you hear me now?
Yes, we can.
Can you hear me?
Yes.
Okay, sorry, but it's probably some mistake on the probably I pushed some button. It's not it was not right. In my presentation, I want to show to you some example of you can use ozone in post-harvest in particular, or but you can use also ozone in water application, for example, for washing fresh cut salad and so on. If you use ozone in particular in gas in the storage room, you can achieve a reduction of the microbial load. You can increase the storage time and the shelf life, and you can have a mycotoxin reduction as pathogen, but also aflatoxin and so on. And you can achieve these goals without residuals on the fruit and vegetable. Sure, before using ozone, you need to make a check of the regulation in your country, because different countries have different regulation of application of ozone in fruit and vegetables. And also you need to check for safety regulation, because some concentration of ozone, as Tony has explained very well before, could be irritant or toxic. And also you need to check the material compatibility on the place where you want to use ozone. If you can use ozone, you have the two big added value that you can have is the extension of the food life, of the shelf life of the products, in particular for climateric products, which meaning that ripening with ethylene, and more safety products, because you have less bacteria, yes mold, yes yeast, and also less mycotoxin. We can see here one example using ozone in apple. As you can see here, ozone sanitation has demonstrated the reduction of microbial loads on apple. You can see the charts. The charts plot days and the colony forming units with ozone and without ozone. As you can see, the condition with ozone give to you the possibility to have 90% less of fungi after 60 days, after 2 months. We ended the test after 2 months, but sure the fungi level will be less when you use ozone. This meaning that if you have less fungi, you have also less mycotoxin. because you know some fungi, as aspergillus and other kind of fungi, produce mycotoxin, and you can find this mycotoxin on the products. We make some tests, and there is a lot of company using ozone in small fruits, berry like blueberry, strawberry, raspberry, and so on. In this presentation, I show to you two different kind of application. The charts show microbacterial loads, column forming units for grams, versus days of storage, with two different regimes and the control without ozone. The two different results was 2 ppm for 5 minutes, high concentration for a short time, and less 0.3 ppm for in continuous way for 7 days. As you can see, we have good results on both. If you don't use ozone, the bacterial load grow very fast, in particular in this kind of fruits. And if you use ozone plus high concentration for short time or lower concentration for continuous for 7 days, you have in both cases very good results. We try to do tests on other kinds of fruits, in this case, for example, grapes. Also, in this case, we try to check ozone in continuous ways and ozone pass. I show to you the results in low concentration in continuous days. 0.2 ppm for 20 days at 1 Celsius degree. As you can see, we have very good results because we have a decrease in disease severity and diffusion. And these results making unnecessary the use of plastic bags or sulfur dioxide. And this happens not only for the grapes that you can sell for the consumer, but also for the grape that you can use for making wine. And this it is very important because now the winery wanted to put less sulfur dioxide inside to the wine for making preservation on it. This is another case in another products. We try to do some test for asparagus because there is a lot of country, for example, in particular South America or also in Italy, that make this kind of production, and they want to send this production to other country. They need to storage for more time, and also it is important making a longer shelf life for all these kind of products, melon, strawberry, blueberry, and so on, because you can manage the sales price. It's not a problem of shelf life for the consumer, but also if you can manage the shelf life of the products, you can decide where you want to sell these products. You can wait when the price go up, and you can sell the products where the price are higher. If you don't use ozone, you need to sell the products in the less time because you microbial load grow, because the product low consistency. In this way, using ozone, you can take time for your customer, take time for the transportation of the product, take time for waiting that the price go up for that type of products. We are discussing before, there was a question before about aflatoxin, mycotoxin, other kind of mycotoxin. In this slide, I show to you that if we use ozone in storage room, we can control the proliferation, the growth of molds, in this case Penicillium expansus, and consequently we can control the contamination of pathogen, because you know normally mold produce pathogen for kill bacteria and eat all the product from the self, okay? But these mycotoxins are also dangerous for human health, especially to children, because they are small. In Europe, we have a high control on pathogen and other mycotoxin in milk, fruit, juice, and so on, in particular for baby food. If you make a control of the growth of the mold in the storage room during the storage, you avoid you avoid the formation of mycotoxin. As back before, it's better to prevent than remove. It's more simple. In this way, if you use ozone, you make a prevention activity that avoid to you to have a problem of mycotoxin of the products. In this case, the ozone treatment process consists of ozone concentration of 0.3 ppm during the night and 0.1 ppm during the days, because if some people need to go inside to the storage room and so on, during the day, the company use less concentration of ozone. As you can see here, we can see the level of pathogen mycotoxin on the products, and as you can see, if you use ozone, you have no developing of mycotoxin. If you don't use ozone, after 1 month of storage, the mold starting grow. You cannot see on the products because it's very small, but the formation of pathogen and other mycotoxin can start, and you can find these products with mycotoxin on the fruits. And it's not simple to detect it, because if you don't make test, you don't find, because you don't see the develop of a mold on the products. As you can see in the picture, on the picture you don't see nothing. But if you make a test on the apple, you can find the pathogen on it. In this slide, I show to you another effect of using ozone on apples, but also you can find it on grapes and strawberry and other kind of products. If we use ozone on an apple or a melon, a grape storage, and if we put these products outside from the storage room, outside from ozone, after that this product come outside from the storage room, the shelf life was biggest. In the case of the apple, for example, was double. In comparison with the product that the same kind of products, the same time that was stay in a normal storage room, the products that stay in storage room with ozone have a shelf life double, not inside of a storage room, outside. We made a lot of tests to understand why, and we think that there is probably several factors. Sure, there is a minor attack of microorganisms, as you can see from the picture, but also there is a possible development of systemic resistance due to use of ozone. You know, ozone is an oxidant, but the fruit was made from live cells. If you make an oxidative stress on this, the cells respond to this, developing a systemic resistance against the oxidation. And when you put these products in normal air, when the level of oxidation is low, the products stay well, have a bigger shelf life. We made the same study after this test on the apple, also to other products, for example, citrus and so on. And in fact, we find that ozone act on mechanisms related to plant defense, especially, for example, for systemic acquired resistance. We find the modification of the products on this, and we find that ozone induce systemic resistance, and this is very good because you have products with more antioxidant inside. And for example, we discussed before about winery, it is very important to have grape with more antioxidant inside. This is important for nutraceutical food. This is important if you have wine, because you have antioxidant, you need to add less sulfurous and so on. On strawberry, we can see some results on strawberry. As you can see, in this case, we use 5 ppm for 24 hours. As you can see, as you know, we use different concentration for different time, because for different kind of products, we need to manage contact and time concentration in a different way, because all the kind of products is different. The concentration for melons is different from the concentration of strawberry, from apple, from kiwi, and so on. And also you have another difference made from the time that you can use ozone. If you needed longer storage time as apple, you can use lower concentration ozone in continuous way. If you have very few time, as in case of strawberry, 1 or 2 days storage before sending out the products, you can use higher concentration and take days for send the product to the final customer. And as you can see, after 10 days, the strawberry storage with ozone was very in a good condition. As you can see from the picture, you can have problem with hydration, but don't have problem of mold, mycotoxin, and so on. I think you can see better in this way. Also, you have, if you have make storage of strawberry at 20 degrees, not in a frozen room, not at low temperature, and you use very few amount of ozone, 0.1 ppm of continuous ozone, you can control the mold. You have damage to strawberry because they stays 5 days at a normal temperature. You can try in your home. It's very difficult to conserve a strawberry and the other small fruits, okay? But if you use a continuous zone, you can see that also on the damaged fruit, you don't have developing of molds. Another goals, another advantage using ozone in storage room or during transportation of fruit and vegetable is that ozone making oxidation of ethylene. You know, there is some products that ripening with ethylene, climacteric fruit, and so on. We can see, for example, here some products. And if you use ozone making oxidation of ethylene on the storage room. In this way, the products don't ripening. As you can see on the left side, the products stored in cell with ozone don't ripening. This meaning that you can control not only the growth of bacteria and mold on the surface of the fruits, but also that you can control the ripening. When you turn on off the ozone, as you can see in the graph in 20 December, the fruit start producing ethylene again and they can ripening. And if you turn off on the ozone again, you destroy again the ethylene, as for example in 3 of January, and the ethylene level go down. In this way, you can control molds, but also control the ripening of the fruit. You can again sell your fruits when the price is better for you, because you can control mold and quality, but also ripening. You can make ripen the same fruit at the right time when the price is bigger for you. But you need to pay attention, because as you can see in this photo, for example, we can see the effect of anchored use of ozone. If you put too much, if you inject the right level of ozone inside the storage room, you can achieve a good preservation of the fruit. If you push ozone, you can have more antioxidant inside to the fruit, make maybe, which is interesting, for example, for wine, which is interesting for nutraceutical product. But if you put too much, the fruit cannot resist to the oxidative stress and you can damage it. This is the reason why it's important to make tests on the different species of the different kind of fruit, because place an ozonator inside the storage room. I had showed to you some example on fruit, but also ozone is used in table grapes, kiwi, melon, orange, pumpkin, pineapples, bananas, and so on. I don't put to you a lot of other slide. I put in my presentation some references here, but if you have any question, you can do here, contact me, and I can give to you also information about the use of ozone in the other kind of fruits and so on. I thank you for your attention. I'm available for your question.
Thank you, Christian. So we have a number of questions.
Okay.
Most of them, you've kind of touched on some of the topics on terms of concentration, but I'll just kind of go through them one at a time. So you talk about asparagus, but apparently you weren't clear about the concentration of ozone required to achieve the proper preservation of the asparagus. Can you comment on that?
The concentration depends from the products and the result that you want to achieve. For example, if I want only to control the ethylene, I can have no ozone because I can put only the ozone that make an oxidation of ethylene. You have very few level of ozone in the storage room. Probably you cannot detect what you can make the oxidation of ethylene and control the ripening without having high concentration of ozone in the storage room. If you want to achieve result for controlling mold, for example, you need to reach level of 0.1, 0.3, depending from the mold that you want to present. Because as you know, ozone have a selective action if using one concentration at one time. For example, in cheese or salmon or other products, if we want the white mold and not the black and the dark, we can use 0. ppm for have the white and kill only the black. We can use 0.3 for killing all the kind of mold. Normally, you go to level 0.1, 0.3, 0.5, depending for continuous treatment of the storage room. In this way, you can control the growth of the mold. Difficult to achieve log reduction of bacteria and mold on the surface. If we want to achieve a results in terms of reduction of bacteria and mold on surface and induction of resistant antioxidant development and so on, you need to go to 1, 5, but this is not possible for each kind of product. If you go to 5 ppm in an apple, probably you destroy it. I don't know if I answered to the question.
Yeah, I think there's a more general question here about concentration overall. We had one person who apparently had some experience with oranges, successful experience treating oranges with ozone. But he wanted, I think, a more general explanation about concentration. But from your talk, it sounds like it's really kind of experimental. In other words, you have a particular fruit, you need to know what you're trying to achieve, and then do some experiments to arrive at the proper concentration, correct?
You're right. We also have a lot of customers using ozone in lemon, orange, and so on. And for example, for control mold on orange, you can use 0.3 ppm. But for give to you an example of the concentration, because the parameter is concentration and time. If you store or in south of Italy, I'm from Italy. In Sicily, we have a lot of orange, for example, in Calabria, in Puglia, in the region of south. There is some company that stores the orange for 1 month, 2 months. And there is other company that stores the orange for 6 months, 8 months. And this is very important because you can sell the products after a lot of time at a higher value. But if we want to preserve the ozone, this orange fruit for 2 months, we can use it 0.3, 0.5 ppm. But if you want to store the 8 months, 6 months, it's better to use lower concentration because the concentration for time is bigger because the storage period is longer, and you can make damage on antioxidant inside to the product. You don't see damage on the surface. Sometimes you can see also some damage on surface because the orange, the lemon have also oil on the surface, no, that give the flavor and so on. But in particular, you can find damage in the antioxidant if you use wrong concentration of ozone. This is the reason why you need to test and adjust the concentration time on the products, on the species orange, because there are different species of orange, and also on the hypothetical storage time that the potential customer want to use ozone.
Thank you. Another question has to do with how you're calculating concentration in the gas phase. Probably what they're asking is this a volumetric calculation or a weight calculation?
Normally in storage room, you make calculation of ozone with sensor, electrochemical sensor, chemistry sensor, that depends, because it's not simple to measure ozone in storage room because there is high humidity, high ventilation, less temperatures, depending from the sensor. Normally we check it in ppm, this meaning, for example, 1 ppm is 2 milligram plus or more for cubic meter, okay? And we use this, when I tend to use 0.3 ppm, this means 0.6 milligram plus or more for cubic meter in a storage room. And we check it with sensor because it's not difficult to make a calculation of the concentration, because also when you make I find a lot of customers try to use in ozone, buy ozone generator and put in the storage room, and ozone don't work because there is no ozone storage room, because normally the people make their company or have difficult to calculate how much ozone do you need for storage room, because it's not a simple calculation to do.
Okay. Another question that came in had to do with the ozone pulse cases. When you talk about ozone pulsing, are you talking about multiple pulses over a period of time, or is there a single pulse and then you just allow the ozone to decay with time?
Normally, when I talk about the pulse application, for example, we talk about to put ozone 2 ppm for 24 hours and leaving ozone and making injection continually of ozone for stay at 2 ppm for 24 hours, and after we leave that ozone decay. Ozone in storage room, it is there is cold temperature 1-2 degrees. Ozone decay slowly for the temperature, but in reality you have a bigger surface because you have a lot of fluids or level of contain beans and other containers that make a reaction with ozone, and you ozone go down very fast if the storage room is full of fluid. And when I talk about pulse for 2 hours, this meaning that we inject continually ozone, make a control with sensor to achieve have this concentration stable, because it's not so good that the concentration going up and down because you can damage the products. And when we want to stop the treatment, we turn off the generator and leave that ozone decay. In some cases, there is some way to make a destruction of ozone with some catalyzer, but very few cases.
Okay, thank you. The next question has to do with safety and regulatory environment regarding the use of ozone. In general, if people are going to be exposed to ozone, what levels are you limited to?
That's a good question. Depending from regulation, depending from country or country, also for application of food, but stay on for safety products. Normally, when one company uses ozone in storage room, they have a signal, a red light, and or other signals out of the storage room that tell please don't enter if the red light is turned on. And there is same safety issue, for example, if people open a door, the ozone turn off and so on. Normally, if you go inside the storage room at 0.1 ppm for very few minutes it's not so dangerous. But normally we try to use level with no more than 0.1 ppm if the people go inside for few minutes. If the people need to go inside and outside for all the day, normally it's better to go to lower concentration, 0, 0.5 and so on. There is a lot of safety level you can find in a lot of publication I can share, is not a problem with you. But where there is all the safety limits, 8 hour working, all the day inside with ozone, only 1 hour working, half an hour working, and heavy work or not, and you can find all this value of for safety people. In these cases, during the night, you can use higher concentration because the people don't go inside. For apple, you can use 0.3 ppm for mounts because normally apple was stored in a storage room and the door was not open for 3 months, for example. When you know that the people go inside outside continuously, you need to use less concentration. This is the reason why in some slides I show to you 0.3 ppm during the night, 0.1 or 0.05 during the day, because sure it is better to have a level of ozone stable, for example 0.3, but if the people go inside to a storage room, we need to turn off the ozone generation during the day for avoiding safety problem.
Okay. And the last question is, in terms of the nutrients associated with the fruit, do you observe changes in the nutrients with the use of ozone?
Yes and not. If you use the right concentration, nothing happens. You only control the grow mood, but nothing happens to the nutrients. If you use high level, too much high level of ozone, you can destroy nutrients, in particular antioxidants. If you're using the right level and the high school level of using ozone, you can improve the nutrient of the products, for example, antioxidant in some kind of products, depending how much you're using ozone in a good way.
Thank you.
You're welcome.
Well, I'd like to thank all of the speakers today who participated. Nicole, can you tell everyone where they can find this presentation and how long it will be available?
Yes, we're going to be uploading it to the IOA-PAG.org website. We will follow up with an email after it's uploaded, so you'll have access to it there.
Okay, thank you very much. And thank you everyone who participated and who came to listen.
Thank you.
Nicole, you can close the webinar.
Thank you all.